I'd like to welcome you to the Chemistry Magic Show. My name is Dr. Ron Furstenon. We're here representing Cool Science, and this is Stacy Lizelle representing the Air Force Academy STEM Outreach Program. And we're going to do a Chemistry Magic Show for you today, a little abbreviated form that we've usually done on Carnival Day before. It's very different with all of you here in person, but we're hoping that you'll enjoy this on the camera here nonetheless. We like to start out in this first demonstration, we like to start out with what we call our Patriotic Demo, our salute to the red, white, and blue. And I have a volunteer, Kelly, that's going to come up here. If you come behind me, Kelly, here. And we like to start out with showing you the bottle here that says Patriotic Solution on there. And what does it look like we have in there? Water. Yeah, it does look like water, but it's not. And that's a very important thing to remember about when you're working with chemicals. So many of them look like water, but they're not. So you never drink them or taste them or do anything like that. And so what we're going to do is you're going to do a salute to the red, white, and blue. And I'm going to take the top off of this, and I'd like you to pick it up with the hand that you'd normally pour something with. And then with your other hand, I'd like you to hold the bottom of this test tube right here, and then pour it about 2/3 of the way up. And I'm going to go look for the red stuff over here. I know I put it somewhere.
Oh.
Whoa, 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 whoa. Wow, how did you do that?
I have no idea.
Wow, Kelly, that was pretty amazing. Go ahead and do the second one. Do the same thing. I'll go look for the white stuff here. See, it must be somewhere.
Whoa.
Whoa, 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 whoa. How did you do that?
I have no clue.
Well, Kelly seems to have the magic touch here. I'm not going to bother to look for the blue stuff. Go ahead and finish it, Kelly.
Wow.
All right, very, very nicely done. And so that's our red, white, and blue salute. Now for the next one to complete it, we're going to do a one-gun salute to the flag as well. And I'm going to move these off to the side here, right? And I'm going to move our one gun, if you will, to the middle here. And I'm going to have you put these on. Now what I have inside of this Coke bottle right here for our one-gun salute is a mixture of two gases. One of them is hydrogen and the other one is oxygen. And they are moving around in there. They're in the gas phase. Gas molecules are very, very far apart. Now, in the patriotic demonstration that Kelly had just done for us, in a liquid form, what they were, the molecules are running into each other a lot. And it kind of makes sense when you think about it. To get any sort of chemical reaction, the molecules have to run into each other. They have to collide. Doing that a lot in the previous experiment, not so much here, but still a lot. If we could piggyback on one of the hydrogen or oxygen molecules in here, it's hitting somebody else about 1 billion times every second. When they react, the H2 and the O2 form water. H2O, simple reaction. But right now, none of them are hitting each other hard enough to actually do anything. But Kelly's going to change that. She's going to light a match to it. The match is going to get some of them very excited, and they'll start to react. They release a lot of energy, which gets the other ones more excited. And because they're hitting each other 1 billion times a second, we're going to get this runaway chain reaction that shoves all the air out of the way, creates a shock wave, and explodes. All right? So if you put those on, Kelly, I'll give you a match here. This is what I'd like you to do. When I give you the signal, I'd like you to light the match. Once I see the match is lit, you're going to see me take the stopper off the bottle. You're going to see me cover my ears. And then you're going to hold the lit match horizontally over the lip of the bottle and try not to let go. All right, so go ahead and light it. Oops, that's okay. That happens sometimes.
Seem to get it too.
There we go. And wait till I cover. Go ahead. All right, very, very nicely done. She did a nice job. Most people are actually unable to hold on to the match here. Now, if you watched it really carefully, it might have been hard to see because of the lighting. You saw a whitish blue flame coming out of the Coke bottle. Very, very hot, over 4,000 degrees, hot enough to melt metal. You may have seen this before if you've seen pictures of the space shuttle launching. If you look at the tail section, you'll see that same color of flame coming out of there because they used the same chemicals as the rocket propellant, right? They used hydrogen and oxygen, but they used it in a liquid form so they could store more. They stored a lot more. There was about 1 billion times the amount of hydrogen and oxygen on the shuttle than there was in here. So Kelly, very nicely done. And Stacy's going to do our next demonstration here.
Right, guys. So you're gonna see a bunch of different demonstrations today, and we're gonna be using all things that look a lot like water. Now I need a volunteer to come on over, so I'm gonna use Connor. So come on over here to my right here, Connor. How are you?
I'm good. How are you?
Good. We're having fun. So Connor, something very important Dr. Fresno brought up. What does it look like?
Water.
It looks like water. They look like water. A lot of things look like water, but like Dr. Ron said, doesn't mean it's water. So what we're going to do, Connor, have you ever broke a bone?
No.
That's good. If he did, we got the remedy for him. Connor, what I want you to do is take one in each hand, pour them simultaneously into that Pilsner flask.
Okay.
Yes, please. And Connor's already pouring like a chemist, doing a great job. Now, Connor, do we see anything happening in there? Not yet. We don't see anything happening at all. These might actually just be water. Well, this demo is not doing what we wanted today. We're going to put this one to the side and go to another one. Now, again, Connor, what does it look like?
Water.
Looks like water. Same thing, right? Hopefully this time it's not just water. We're going to see if Connor has any magic abilities. I'm going to give you a wand, and I'm going to use one. And we need a magic word.
All right.
What do you want to use?
Ciao.
Ka-chow. So what we're going to do, Connor, to this, hopefully not water this time, we're going to go 1, 2, 3, ka-chow.
All right.
Evidently, I do not have the touch today. So Connor, hopefully you can get it to work.
1, 2, 3. Ciao.
Whoa. Connor, what did you do? Maybe I should have had you do the last one. Now I want you to hold that in your hand and tell them what it feels like.
Warm.
So something else has happened though. Hold that there and turn it over. It's solid. What did you do?
I don't
The
know.
force is strong with Connor today, evidently. I should have left him alone with the last one. He probably could have got it to work. Now we'll let Dr. Ron take the next one.
Right. And thank you, Stacy. I'd like to go back to this one a second. And very often we don't explain every one of these demonstrations that we do, but I'd like to explain this one to you. This is one of my very, very favorite demonstrations. This is a supersaturated solution of a chemical called sodium acetate. Sodium acetate is a fairly common chemical, and it's used in one form or another, for example, to give flavoring to salt and vinegar potato chips. It will give it that vinegary type flavor. But this unusual compound in that we can supersaturate it. And what that means, it's kind of like dumping sugar into iced tea at a restaurant. You'll see people keep dumping sugar packets, and then it doesn't do any good anymore because it saturates it, and the sugar just sludges to the bottom. Now, in warm water, you can dissolve more sugar, and sodium acetate is the same way. So we dissolve it in water at a higher temperature and then saturate it, supersaturate it at a high temperature, slowly cool it to room temperature, and it will stay in solution until it's disturbed. Now, what happened was that Connor's wand had a small solid crystal of it in here, and Stacy's did not. When he hit it on there, the crystal fell in, and the rest of the crystal grew around it. Now, to regenerate this, all we do is just heat this up in boiling water. We probably had this particular one for 20 years. And these are, because he felt it was warm, this is actually used in a little bit different form in a plastic bag as hand warmers that you can buy at outdoor stores. Now, for the next demonstration we're going to do, I need Kelly to come back up here again. Now, Kelly, what does it look like we have in here?
Water.
Now, it kind of looks like water, but it's not. These are very special chemicals that if Kelly can get all of the molecules moving in the correct direction, the molecules, when they collide with each other, they'll collide just the right way, have a chemical reaction, and turn a nice dark blue color. Now, in order to make that happen, you have to turn it clockwise. So go ahead and do that. All right, that looks good. I'm pretty sure that's right. Okay. Now, I'm going to pour these in. Then I want you to stir it clockwise. And then by the time I get the caps back on, if you do this correctly, it should turn blue. Nothing's happening. I got the caps back on. Let me think about this.
Ron,
Oh, no, I know what's wrong.
we're south.
We're south of the Air Force Academy. It has to be counterclockwise. Go the other way. I'm going to stand over here. I don't know what happens if you get it going in the wrong direction. Keep with it. I'd like you to stop. No, put the rod back in. Pick up the rod. There you go. Very nicely done. Sorry, I told you the wrong way. You can have a seat back there, Kelly. This is also one of my favorite demonstrations as well. This one's called the Iodine Clock reaction. And in this particular reaction, there's a couple of reactions going on sequentially. The first one is what we call the rate determining step. It's a very slow chemical reaction, and it's producing products that don't have any color. Now, the reaction that causes color that we need, it's a very fast reaction, but it cannot occur until the other one is finished, all right? And then so once that one is finished, the second one that's very fast there's a couple of reactions that are very fast that result in the products that make it turn this blue color. And we can adjust the speed by putting in certain amounts of other chemicals. And this is a very, very fun one for me. And Stacy, you've got our next demonstration.
All right. In this very warm studio today, I think I'm going to actually work with something Dr. Ron made an allusion to earlier, which was the cryogenic fuels used in the space shuttle. So since we do not travel with liquid oxygen or liquid hydrogen, probably not the best thing to have in your car, and I can't afford the insurance, we travel with liquid nitrogen. Connor, if you want to come on over again. So nitrogen is the primary component in the air that you're breathing. And what we do at the Academy is we have a special machine that's able to take that nitrogen out of the air and compress it, condense it into a liquid. Now, as I pour this out, Connor, I want you to describe what you see happening.
Kind of like bouncing up.
Yeah. It looks like it's boiling. That seems kind of weird though, right?
Yeah.
It is boiling. Liquid nitrogen becomes a liquid at about 300 degrees below Fahrenheit, about 200 degrees below centigrade. So this tabletop, because it is warm in here right now, is really hot like an oven. So it is boiling. And Connor, you can put your hand real close. Don't touch the glass, but just get real close here. And you can feel how cold that is.
Yeah.
Actually, it feels kind of nice right now, doesn't it? It's pretty warm in here. So this is an example of how we take gases and turn them into liquids. So in the space shuttle, the oxygen would be condensed into a liquid along with the hydrogen. And they would put those in to the huge orange tank in the space shuttle, pretty close to right before launch. So you'll see a lot of this steam coming off, which is actually water vapor. It is so cold, it is condensing what little water we have in the air in Colorado, because it's pretty dry here, and it's turning it into water vapor, and that's what you see coming off here. Now it's starting to settle down a little bit, but the volume's gone way down. The nitrogen's going right back into the air where we got it from. Now we can do some experiments with this. We're going to start with a simple one. This is a simple balloon that we filled up. Now, as part of physics, we should just remind you that the reason this balloon stays inflated is because there's a higher pressure inside, and then we have it closed off. If it was room pressure, the same pressure it is out here, the balloon wouldn't be inflated. Now, Connor, what I want you to do is hold it there, and then slowly put it in there and watch what happens. You may have to put a little more nitrogen in. Now try it again. Oh, what's happening? What happened to the balloon? Where did all the air go? That's kind of crazy, right?
Yeah.
Where did it go? Now something else is happening. It's starting to reinflate. Is it magic? Kind of. Magic is just science you don't understand yet, right?
Yeah.
Connor's a NASCAR fan, so he can appreciate it when I say velocity. But what's going on is we're affecting the velocity of the molecules inside the balloon. So when he gets it in the nitrogen, the average velocity of the molecules is really slow. They don't move very much. They take up a lot less volume. So it looks like the balloon is deflated. As they start to warm back up again, if you want to set it right there, like in a NASCAR race, they're going to start moving faster and faster and faster, and they're going to reinflate that balloon. Moving really slow right now. Getting there. Now, something to consider when you're doing engineering and thinking about the materials you're going to use to hold cryogenic liquids in a rocket, you need to make sure that your materials can handle the extreme cold. If this balloon gets cold enough and we let it sit in there for a while, I could crack it with my hand. Probably something you don't want to have happen when you're launching into space. Now, something else we can show you. I'm going to grab a flower. And go ahead and give that a feel. Right up here. How's it feel?
Pretty soft.
Pretty soft. Now feel your cheek. You're soft.
Yeah.
What do you think? Yeah, it's water. So the flower is mostly water. We're mostly water. So it feels soft because of that water. So you can think of little bags of water, big bags of water. Now what happens to water when it freezes? Yeah, it expands and it cracks. What we're going to do is we're going to take this flower and I'm going to freeze it. It's only going to take about 3 seconds. And then you're going to clap on it. So we'll practice real fast. So I'll take the flower, we'll pretend I dipped it in there, and you go ahead and clap on it. Nothing exciting right now, yeah? Just soft.
Yeah.
So 1, 2, 3. Try it again. And do it again. And how does it feel?
A little hard.
Kind of like frozen potato chips, frozen
Yeah.
glass, tiny pieces of ice. We've heard a bunch of different explanations. We froze all the water. Now we could take Connor's hand and do the same thing. We don't do those experiments anymore because it's really messy. But it would do the same thing because we're mostly made out of water. It just might take a little bit longer. So those are some of the advantages and disadvantages of using cryogenic liquids. You have to take certain precautions, but they do amazing things. These fuels otherwise would not be available for the space shuttle because as a gas, they just take up way too much space. Now I'm going to move this out of the way so Dr. Ron can do his next demo.
And
Don't
Stacy,
wanna
I'm
grab this
going to actually have you leave it there because
no,
I'm going to use
perfect.
it for something.
Perfect. You want?
All right.
I'll take
And
the
if you
flower.
would take this.
Sure.
All right. Great. Thank you. Now, this is extremely cold, the liquefied nitrogen. If you wonder how it's actually changed into a liquid, I'm going to have you do a little experiment with me at home right now. If you take your hand and open your mouth wide and blow on the palm of your hand, you'll feel that it's warm. Go ahead and try that. Okay? Now do the same thing, except pucker your lips and blow. And you'll notice it's cooler. Now, that's how we liquefy something like nitrogen from the air. About 80% of the atmosphere is nitrogen gas. So to make the liquefied nitrogen, we remove the other things from it, mostly oxygen, a little bit of argon, and then we compress the gas in a pump. Then we pass it through a little hole, and then that cools it down. We compress it in a pump again, pass it through a little hole again, and it keeps cooling down until it eventually changes into a liquid. And Kelly, if you'd hand me that little styrofoam container. Now, we have a very, very cold liquid here. In fact, it's about 320 degrees below 0 Fahrenheit, about minus 200 degrees Celsius. I also have something cold in here that's a solid. And I'm going to take this paper towel and grab just a small piece out of there. I don't want to grab anything in here with my bare hands, but the paper towel will be fine. I'm going to set it on the paper towel right here, and so it doesn't move away. And what we have on here, you can see this white solid. I'll kind of put it here so it might be easier to see, is a chunk of frozen carbon dioxide. Now, carbon dioxide is normally a gas at room temperature. It's one of the gases that you exhale when you're breathing. Now, what I'm going to do here with this, if we contrast it with a piece of water ice, if I set a piece of water ice on the table right here, eventually what would happen, it would get enough energy from the table to change the water, the ice into water, and then we'd have a little puddle there. And then the puddle, if we left it there long enough, it would eventually go away, it would evaporate. Now, frozen carbon dioxide at this pressure does not do that, right? It goes directly from being a solid into a gas. It skips being a liquid, which is why it's often known as dry ice. So I'm going to do a little experiment here, and we're going to explain why it does that. Now, I've got it on the paper towel, but now I'm going to put it on this table here, and hopefully you'll be able to hear something. You can hear it, and you can see it vibrating up and down. You can see it moving as well. Now, the reason that it does that is because the table is warm, it's subliming. It's forming a layer of gas between the table and itself, and that's what makes it move, kind of like a hockey puck on an air hockey table. It's making noise because it starts to get the table cold enough So it lands on the table, might move a little bit, it lifts up again, goes down, lifts up, and that's why it's making the noise that it does. Right? Now, if you would hand me that flask there with that one. Now, we're going to do an experiment that shows you there really is gas coming off of it, even though we couldn't see it in the previous experiment, right? And I want you to think about what's going to happen here. I have this liquid right here. It's mostly water in there. And I have this chunk of frozen carbon dioxide. What I'm going to do is I'm going to slam it on the table here to break off a smaller piece. There we go. And I'm going to put it inside of here. We should think about what's going to happen. Let's see if it does. Now, if you look at it very carefully, you can see that we have bubbles coming out of there. That's because the water is much, much warmer than the frozen carbon dioxide. The frozen carbon dioxide is probably about 110 degrees below 0 Fahrenheit. Water is probably about 72 degrees above 0 Fahrenheit. So it's causing it to sublime. So it's going from a solid to a gas. That's the bubbles that you can see. Now, if you look at it very carefully, you'll notice that the bubbles look white. The reason that they look white is that the gas coming through there is so cold that it's causing water to condense inside of the bubble. The bubble gets to the top and it breaks, and it releases the little cloud in the form of this smoke. Very, very tiny water droplets that are so tiny you can't even feel them. Now, we're going to do another experiment here. And this might be a little bit harder to see, but I want you to all think about what might happen here. I have the liquid nitrogen. It's at minus 320 degrees Fahrenheit. And right now it's kind of simmering in there. I have the frozen carbon dioxide that's at about 110 degrees Fahrenheit. We have a liquid here, we have the liquid there. I want you to think about what's going to happen. Now, you'll notice it's bubbling, kind of like this one is right here, all right? And really for almost the same reason. Now, we're not getting as much smoke coming off of there because this is not water. It cannot cause the nitrogen vapor to condense because the bubble coming out of there certainly isn't cold enough. But it is bubbling, and it is bubbling for the same reason, for a little bit different reason than it is here. The bubbling is not from the carbon dioxide. The carbon dioxide, even though it's at 110 degrees below 0 Fahrenheit, it's much warmer than the liquid nitrogen. So when we put it in there, it's like I put a boiling piece of steel into some very, very cold water. And that causes that water to boil. And that's exactly what happened here. That very, very cold frozen carbon dioxide is really, really warm compared to the liquid nitrogen. And it made it boil over. And now it's kind of simmering here because it's cooled it down enough that it's at about the same temperature as the nitrogen. So that's one of my really favorite ones. And I think, Stacy, we have enough time to do one more experiment
All
for
right.
everybody. And that'll be yours.
All right. All right, for our final experiment, we're going to use our 2 volunteers and everybody out there watching. So Kelly and Connor, if you guys want to both come in. Once again, we have stuff that, what does it look like, guys?
Water.
But
It's not.
it's not. All right. Now what we need to practice something really quick because this is going to sound really strange, but it enjoys good energy coming from people. So if you tell it to do something, it just might do it. So Kelly, do you want yellow? You want gold or do you want blue?
Blue.
You're going to go for blue. So Kelly and all her friends out there watching are going to be cheering for blue. Connor, you get gold.
All right.
So you and all your friends out there are going to be cheering for gold. You guys want to practice? So pretend it's all in there, and then you're going to yell, blue, blue, blue. And Connor's going to yell.
Go.
Does everybody get it? Okay, we're going to take this, not just water chemicals. I'm going to pour in the first one, then you two can simultaneously pour in the second ones. And then right away, you got to hit it with that energy. So go ahead.
Go.
Hope everybody's
Blue,
ready.
Go. Go.
Oh, Connor's going.
Blue,
Oh,
come
Come on,
on, blue.
go.
Come on, blue.
oh, you better give us some energy.
Come
on,
on,
go.
blue. Come on, no.
There it goes.
Oh, there's the blue. All right, Kelly.
Come on, go.
Come on, blue.
Come on, go.
Go.
Yeah, come on, gold.
Come on, Blue.
Come on, gold.
I hope your television friends are helping. Does anybody want to do magic fingers? Heart stare?
Come on, Blue.
I know. Thank you, cameraman.
Come on, Blue.
Let's go, gold.
You guys, help them out there.
Go.
Now you guys are going to notice something's happening, and you might be able to see this on your screen. What do you guys see happening in here?
Bubbles.
Bubbles! So we've seen bubbles with the liquid nitrogen. We've seen bubbles with the water and the dry ice. Bubbles show us a trapped gas is being evolved, right? You may not know what the trapped gas is, and that's okay, but that means something's leaving. So this is called an oscillating reaction, which means to go back and forth. And even though Connor's cheering for the gold and Kelly's cheering for the blue, the funny thing is, guys, the blue chemical makes the gold, and the gold chemical makes the blue. So even though out there in TV land, they're hearing blue, 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 gold, you're cheering for the opposite of what you think you're cheering for. Now, in an oscillating reaction, like I said, it means it's going to go back and forth. Now, you think, is it going to do this for the rest of eternity, for the rest of today? The answer is no. There's no such thing as a perpetually oscillating reaction. It is oscillating, and eventually will settle at equilibrium. It just takes a really long time. Oscillating reaction. We'll end up actually making iodine crystals because the blue color is a compound that forms with iodine. So this is the oscillating reaction. Dr.
All right.
Ron, anything you'd like to add to that
Well,
one?
we would like to thank you for participating in the Cool Science Festival, the virtual Cool Science Festival Carnival Day today. We know it's not the same as being in person and interacting with you, but we are very glad that the Space Foundation is hosting us here today to do the video, and the Space Foundation also has a lot of great activities going on today, and so really feel free to come down here if you're in the area and have a lot of fun. So we want to thank them for hosting us here today for this live demonstration, and we'll be back for about 20 minutes later this afternoon doing some more chemical magic. So on behalf of Stacy and myself and Kelly and Connor, thank you very much for attending today.
Thanks, guys.
Bye-bye.